Okay, let's jump right in. Welcome to today's Explainer, where we're tackling a massive and honestly highly misunderstood topic in manufacturing: recycled plastic compounding and color matching. Look, if someone ever tells you that color matching with virgin raw material and color matching with recycled plastic is the exact same process, well, they probably haven't spent much time on an actual production floor, seriously. Treating recycled plastic like it's this pristine, virgin material, that is a massive production mistake. And today, we're going to look at exactly why that is. So take a look here. On the left, you've got virgin raw material, right? It's predictable, it's clean, it's basically a blank canvas. But then on the right, you've got recycled plastic. And if you're only focusing on getting the color match right here, you are totally missing the forest for the trees. Working with recycled plastics is a deeply complex science. We're talking contamination, material degradation, rigorous process control. It is absolutely not just about getting the shade right. It's about understanding the core material science behind what makes recycled plastics so incredibly unpredictable. Here's our quick roadmap for this explainer. We'll start by defining PIR and PCR, then we'll look at the history of plastic, tackle those nasty color matching roadblocks, discuss how to control contamination, break down a real industry case study, and wrap it all up with the ultimate R&D checklist. All right, Section 1, Understanding PIR and PCR. Let's get into it. So the first thing to know is that not all recycled plastic is created equal. On the left side of our table, we have PIR, which stands for post-industrial recycled plastic. This is the scrap that comes straight from the manufacturing process itself. You know, things like runner regrind, edge trims, or startup waste. It's cleaner, it's incredibly consistent, and honestly, it's relatively easy to color match. But then on the right, we have PCR, post-consumer recycled plastic. This is the plastic collected after consumer use. Think old shampoo bottles, water bottles, household buckets. And PCR? Man, it brings a mountain of challenges. You're dealing with mixed colors, dust, paper labels stuck to it, moisture, and yeah, even lingering odors. Moving right along to Section 2, the history of recycled plastic. This is absolutely crucial to grasp. The biggest difference between a virgin polymer and a recycled one is its history. A recycled material has already survived the intense stress of a previous processing cycle, and because of that thermal trauma, the material physically alters. The melt flow, it can completely change. The base color, often yellows. Its overall mechanical strength drops, and it actually tends to absorb moisture. So what does this all mean for you? Well, it means if you take the exact same color formulation you use for a virgin polymer and drop it straight into a recycled polymer, there's just no way around it. You are going to get completely different and very likely unusable results. Which brings us to Section 3, color matching roadblocks. Imagine a giant batch of post-consumer recycled material arriving at your facility. It almost never looks like one uniform color. A single PCR batch is usually this chaotic mix of multiple colors in flake form. We're talking blue, red, green, black, all just jumbled together in one big pile. Establishing a uniform, predictable base from this random rainbow of flakes, it is an absolute nightmare for any processing engineer. And because of that mixed batch, you're going to run into some highly specific, really technical roadblocks. First off, your base color is almost never perfectly clear or white. It's already got some shade of gray or yellow to it. So whatever color you're actually trying to achieve is instantly going to shift because of that underlying base. Second, the previous pigments from the original products, they can't be fully removed. They act like these sort of ghost undertones that will constantly bleed through and fight against the new color you're trying to apply. So how do we fix this? Well, this brings us to the absolute golden rule of color matching recycled plastics. Never, ever just copy the virgin material formula. Literally, it won't work. The solution requires a strict, scientific approach. You absolutely must analyze the specific base material of the current batch, and you have to run trial molding before you ever commit to a full production run. Let's jump into Section 4, Controlling Contamination. We really need to forcefully debunk a super common rookie myth right now. Contamination is not just a little bit of surface dust that you can just wipe or brush off. When we talk about contamination in recycled plastics, we are talking about severe structural threats to your final product. Check out these true contamination sources. We're talking microscopic metal particles, shredded paper labels, bits of wood and rubber, chunks of burnt polymer from previous heat cycles, and sometimes even entirely different mixed polymers that just snuck their way into the batch. These contaminants cause black specks, nasty surface defects, and they will completely ruin your color consistency. But more importantly, they cause weak mechanical properties. Fixing this isn't easy. It requires heavy industrial intervention, stuff like washing lines, metal separators, melt filtration systems, and sometimes even advanced optical sorting. And since the polymer has already degraded and faced all this contamination, you often have to run what are essentially chemical rescue operations. To actually recover the mechanical properties of the plastic, companies have to rely on specialized additives. You use antioxidants to prevent further degradation, chain extenders for specific polymers to essentially rebuild their molecular weight, impact modifiers to stop the plastic from becoming super brittle, and compatibilizers to help different mixed plastics actually blend together smoothly. It's really like putting together a giant chemical puzzle. All right, let's see this all in action. Section 5, Real Industry Case Study. So this is an actual real-world customer complaint that an engineering team received. The customer called in and simply said, "Black bucket toot rahi hai," which roughly translates to "the black bucket is breaking." Now, to an untrained eye, a breaking product might just look like a simple molding issue, or maybe they used a cheap dye. But let's treat this like the true manufacturing mystery it is. Let's just walk right through the troubleshooting process they used. Step 1. The team checked the color formula. The result? It passed perfectly. The problem had absolutely nothing to do with the color. Step 2. They tested the post-consumer recycled material itself to check for contamination and degradation. The result? It failed miserably. The PCR material was highly degraded. So, Step 3. The solution wasn't adding more pigment. Actually, scratch that, the solution was applying better sorting up front, blending the materials more effectively, and improving the exact chemical stabilizer package we just talked about. The final result? The product passed. The major takeaway here, not every problem you encounter is a color problem. Often it's a deep structural material science problem. Almost done here. Section 6, the R&D checklist. Right before we get to the actual checklist, we need to highlight the most common mistakes operators make when they fail to treat recycled plastic with the specialized care it requires. Applying a virgin formula directly to a recycled batch, that is mistake number 1. But trailing closely behind are skipping the crucial moisture test, totally ignoring contamination checks, paying literally no attention to the melt flow index, or MFI, and simply not verifying the source of the recycled raw material. Listen, doing any of these practically guarantees a failure on the line. So how do we actually avoid those mistakes? By adopting a true R&D mindset. When a professional R&D engineer looks at a new batch of recycled plastic, they instantly ask these critical questions. What is the actual source of this material? How much virgin plastic needs to be blended in to stabilize it? What is the existing base color I'm fighting against? And most importantly, what is the final mechanical target this product needs to hit to actually survive out there in the real world? Compounding and color matching recycled plastics isn't just about tweaking pigments, It is an incredibly demanding exercise in material science. So the next time you look at a simple recycled plastic product, ask yourself, what chemical rescues and processing miracles had to happen just to make it look ordinary? Think about that for a bit, and we'll see you in the next explainer.
Recycled Plastic Compounding and Color Matching Challenge PCR winners PIR. As we reach the end of this video, I want to you imagine something. A truck arrives at a plastic recycle plant carrying thousands of kilograms of plastic waste. At first glance, it all looks the same, but hidden inside those bags are different polymer grades, different processing histories, different pigment, different additive, moisture, contamination, UV damage, and years of unknown exposure. Now imagine you are R&D engineer standing in the front of the material. Your customer isn't asking for excuse. You are asking for one thing. Can you make this recycled plastic perform exactly like virgin material? And that's where the real challenge begins. Every batch tells a different story. One day the melt flow is perfect, the next day it changes completely. One batch the color beautiful, the next batch turn slightly yellow, grey or dull. Even with the same formulation, PCR, post-consumer recycled material, carries the history of its entire life. It has been used, exposed to sunlight, heat, chemical, dust and multiple processing cycles. PIR, post-industrial recycled material, is a clear more constant and easier to control, but even it can surprise you when processing conditions change. This is why recycled plastic compound is not just mixing material. It is a science. It is over variation. It is a troubleshooting and above all its experience. The best compound don't just look at color. They understand polymer degradation. They study oxidation. They analyze contamination. They optimize stabilizer. They balance filler. They improve dispersion. And they keep refining the formulation until the customer can't even tell that the product was made from recycled plastic. That is the real beauty of polymer engineering, turning waste into value, turning any consistency into reliability, and turning sustainability into commercial success. If today's video helped you understand the real difference between PCR and PIR, then remember this is only one chapter in the world of polymer technology. In the next episode, we will dive even deeper into real industrial challenge, advanced compound techniques, color matching, secret troubleshooting method, and a practical R&D knowledge that professionals use every single day in the plastic industry. So, if you truly want to become a skilled polymer engineer, master batch developer, color matching expert, or plastic R&D professional, make sure you are part of this learning journey. Subscribe to the channel, turn on notification, and continue learning with us. Because in polymer engineering, every color has a reason, every defect has a root cause, and every successful formulation begins with the understanding the science behind the material. Thank you for watching. Keep learning, keep experimenting, and I will see you in the next video.